Have you ever wondered how deep learning models, with their millions of parameters, manage to become incredibly powerful without simply memorizing every single piece of their training data? When it comes to dropout, a widely used regularization technique, the rate itself is generally not considered a learnable parameter in the traditional sense. Instead, it is a hyperparameter that you define and tune before or during the training process. The core reason lies in how dropout works and how neural networks learn. Dropout operates by randomly setting a fraction of neuron activations to 0 during each training iteration. This introduces noise and prevents complex co-adaptations between neurons, forcing the network to learn more robust features. However, the decision to randomly drop neurons makes it extremely challenging to compute a meaningful gradient for the dropout rate itself using standard backpropagation. Gradient descent, the workhorse of neural network training, relies on smooth, differentiable loss functions to update weights and biases. The dropout rate directly controls a stochastic process, which does not easily lend itself to this gradient-based optimization. Since the dropout rate is a hyperparameter, its optimal value must be discovered through experimentation rather than direct learning by the model. This involves a process known as hyperparameter tuning. Common approaches include grid search, where you try a fixed set of values, or random search, where values are sampled from a distribution. More sophisticated methods like Bayesian optimization or evolutionary algorithms can also be employed to efficiently explore the hyperparameter space. You then evaluate your model's performance on a separate validation dataset to determine which dropout rate yields the best generalization. It is fascinating to note that while the dropout rate itself is not learned, its impact is profound for model generalization. An interesting implementation detail is often what is called inverted dropout. Here, the activations of the remaining active neurons are scaled up during training. This ensures that the expected output of a neuron remains the same whether dropout is applied or not, simplifying the network's behavior at test time. While standard dropout rates are fixed, active research explores dynamic or adaptive dropout, where the rate might change during training based on specific criteria, though this is a more advanced concept and still involves meta-learning or separate optimization loops rather than being a directly learnable parameter via backpropagation. Ultimately, understanding the dropout rate as a hyperparameter is crucial for effectively designing and training robust deep learning models. It empowers you to prevent overfitting and encourage your network to capture more generalizable patterns from your data, even if it means a little extra tuning effort on your part.